Viewers, my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. And today's topic is a discussion of tutorial question bank of the course Antennas Based on Propagation, Module 2. Today's topic is discussion of tutorial question bank on Module 2, so which belongs to the course Antennas Based on Propagation. So let us start our session. So for a 20 turns helical antenna operating at 3 GHz with circumference of C is equal to 10 centimeters and spacing between the turns is 0.3 lambda, calculate the directivity and half power beam width. So for a 20 turns helical antenna operating at 3 GHz with circumference C is equal to 10 centimeters and spacing between the turns is 0.3 lambda, calculate the directivity and half power beam width. So the number of turns N is given as 20 here and the frequency is 3 GHz. Circumference is given as 10 centimeters. The spacing between the turns S is represented as by the symbol S. It is given as 0.3 lambda. And we need to calculate the directivity and the half power beam width. So we need to calculate the directivity and half power beam width. So here the frequency is given as 3 GHz. So from the frequency you can calculate the value of lambda. So by using the formula, C is equal to F lambda. So lambda is equal to C by F. Is equal to 3 into 10 power 8 divided by frequency 3 into 10 power 9. So 3 get cancelled. So this is equal to 1 by 10. So this is equal to 0.1 meters. So this is lambda value which is expressed in meters. Similarly, this the value of C here can be represented in terms of meters as 10 into 10 power minus 2 meters. 10 into 10 power minus 2 meters. Now, so based upon the data available, so we need to calculate the value of D and half power beam width by using the formula directivity, that is GD max. We are having a formula 15 ns c square divided by lambda cubed. So in this we know that n number of turns is equal to 20 and S is given as 0.3 lambda and C is equal to, circumference is equal to 10 centimeters. We can write as 10 into 10 power minus 2 meters. And lambda, just now we have calculated the value as 0.1 meters. 0.1 meters here. So GD max is equal to 15 into N 20. It is given as 20. And yes, it is 0.3 lambda into C square. So 10 into 10 power minus 2 whole square whole divided by lambda cubed. So lambda cubed is nothing but this is lambda cubed. So here 0.3 lambda and lambda will get lambda square here. So lambda square we can write it as this is 15 into 20. This is equal to 300 into 0.3 into 100 into 10 power minus 4 divided by lambda square is equal to 0.1 whole square. 0.1 whole square. So from this equation, if you substitute and simplify, you will get the GD as 90. You will get the value of GD as 90. So 300 into 0.3 into 110 power minus 4 by 0.1 square, you will get the value as decimal value as 90. So we can also convert this into dB value by the formula 10 log 90. So we can write this as a 10 log 90 based on which we can represent it as in terms of dB. So this is the decimal value and this is the dB representation. Similarly, we are going to find out the half power beam width. Half power beam width is given by 52 by C root of lambda cubed by ns. 52 by C into root of lambda cubed by ns. This is equal to 52 by 10 into 10 power minus 2. Lambda value is 0.1 whole cubed. N is number of turns is equal to 20. And S is the 0.3 lambda. So 0.3 lambda is equal to S. So we can write as 0.3 into 0.1. 0.3 into 0.1. So here half power beam width, if we simplify here, So you will get here 0.1 get cancelled here. You will get the whole square here. So 52 into by 100 means 52,100 by 10. Root of 0.1 square divided by 20 into 0.3 means it is 6. So 20 into 0.3. So 20 into 0.3 into 20 is equal to 23s are 60 here. Point will get 6 here. So this approximately you will get 520. You will 0 get cancelled. 520 into 0.1 divided by root 6. Divided by root 6. So you will get, by simplifying, you will get the value as 21.23 degrees. 21.23 degrees here. So this is the half power beam width. This is the half power beam width is equal to 21.23 degrees. So this is how to calculate the value of GD max and half power beam width. We are having formula 15 ns square by lambda cube, and half power beam width is equal to 52 by c into root of lambda cube by ns. So this is the data given in the problem here. So n is equal to 20, c is equal to 10 centimeters, and s is equal to 0.3 lambda, f is equal to 3 gigahertz, and lambda is equal to c by f. It's equal to 0.1 meters. So if you substitute the data, you will get the values as half power beam width is equal to 21.23 degrees centigrade. The next one is the length of the horn. So here the determined length rho of the horn, H plane aperture, and flare angles theta E and theta H of a pyramidal horn, for which E plane aperture is 10 lambda. The horn is fed with a rectangular waveguide of TE10 mode, and let delta the phase difference is equal to 0.2 lambda in E plane and 0.375 lambda in H plane. Calculate the beam width and the directivity. Calculate the beam width and the directivity. So here we need to have the data given. The data given is given as AE. It is given as 10 lambda. So E plane length is given as the aperture E plane length is given as 10 lambda. And we know that theta E is equal to 2 cos inverse of rho by rho plus delta. So rho by rho plus delta here. So for E plane, it is given as delta is equal to, for E plane, according to the data given, it is given as delta is equal to 0.2 lambda. Also, we are having a formula rho is equal to h square by 8 delta. So here is the height is nothing but the height in the E plane represented as theta. It is represented as AE here by 8 delta. What is AE given? It is 10 lambda. 10 lambda into 8 into 0.2 lambda. So lambda lambda get cancelled here. So if you simplify this, 10 lambda whole square here. If you simplify this, you will get 62.5 lambda. So the value of rho for E plane can be written as 62.5 lambda. So we are having a formula to determine the rho value. So rho is equal to h square by 8 delta. H is nothing but the aperture length in the E plane. It is given as AE. This is h here. H is equal to AE is equal to 10 lambda, and rho is equal to 62.5 lambda. So from this we got the value of rho, and we can substitute find out the value of theta in the E plane by using the formula. Theta E is equal to 2 cos inverse of rho by rho plus delta. This is equal to 2 cos inverse of rho is nothing but 62.5 lambda divided by 62.5 lambda plus it is 0.2 lambda. So this is equal to 2 cos inverse of 62.5 lambda divided by 62.7 lambda. So lambda lambda get cancelled. So you will get approximately 10.25. You will get the value of the theta E, theta angle in the direction of E plane is 10.25 degrees here. 10.25 degrees. Now similarly, we are going to find out the value of in H plane. So in H plane, the data given is according to the problem is given as 0. Delta it is given as 0.375 lambda. So we are having a formula theta h is equal to 2 cos inverse of rho by rho plus delta. Again using the same formula. So this is equal to 2 cos inverse of, we simplified the value of rho as 62.5 lambda divided by 62.5 lambda plus 0.375 lambda. So this is equal to 2 cos inverse of, and lambda get cancelled, you will get 12.521 degrees here. 12.521 degrees. This is the value of theta h. So we are simplifying the values of theta e and theta h. And similarly, the h plane aperture, in h plane aperture, we are having a formula as tan theta is equal to h by 2 rho, or which can be written as AE by 2 rho. So here AE is equal to tan theta into 2 rho. So AE is equal to tan theta into 2 rho. So this is equal to tan theta, the value of tan we got as 12.521 theta. Just now we got as 12.521 here. Theta h. So this into 2 into 62.5 lambda. So overall, if you simplify, you will get 27.7 lambda. So if you simplify this, tan theta into 2 rho, tan of theta is equal to 12.521 into 2 into 62.5 lambda. This is equal to 27.7 lambda. Now HPBW. So as per the given data, we need to find out the half power beam, which is given by the formula theta h is equal to 67 degree lambda by AH. So here theta h is equal to 67 lambda by 27.7 lambda. So if we simplify this, you will get 2.413 degrees. If we simplify this, you will get 2.413 degrees here. Now we need to find out the physical aperture. The physical aperture is given of the horn and is given by the length and breadth of the antenna. So which we are denoting as AE into AH. So length of the aperture in the E plane multiplied with the length of the aperture in the H plane. So if you simplify this, AE is equal to, we are having 10 lambda and AH is equal to 27.76 lambda. 27.76 lambda. So based upon this data, we are going to find out the value of AP here. So this is AP. Now let us find out the directivity. So directivity is equal to 10 log 7.5 AP divided by lambda square. So this is equal to 10 log 7.5 into 10 lambda into 27.75 lambda divided by lambda square. So if you simplify this, you will get 33.18 dB. You will get 33.18 dB here. So this is how to find out the value in E plane. So rho is equal to h square by 8 delta, AE by 8 delta. So from this we are getting the value of rho as 62.5 lambda. And flare angle in the E plane is given as rho by rho plus delta. Substitute the values of rho and rho plus delta. Here you can get 10.25. Similarly in H plane, delta is equal to 0.375 lambda and theta h is equal to 2 cos inverse of rho by rho plus delta. So theta h is equal to 12.521 degrees here. And similarly, the tan theta is equal to h by 2 rho here. From this we are going to find out the value of AH. So this is AH. AH is equal to 2 rho tan theta. We are getting a 27.76 lambda. Similarly, theta h is equal to 16 degrees lambda by AH. We will get 2.413 degrees. And directivity is equal to 10 log 7.5 AP by lambda square. And AP is equal to length into breadth, so which is given as AE into AH. So approximately, if you calculate the value, you will get 33.18 dB. Now calculate the directivity of the pyramidal horn antenna with aperture size of 12 by 12 centimeters, operating with 3.2 centimeters wavelength here. So here we are having a formula. So D is equal to 7.5 AP by lambda square. So the directivity is given by 7.5 AP by lambda square. So what is AP here? So AP is equal to, in terms of meters, if we represent here, we can write as 12 into 10 power minus 2 into 12 into 10 power minus 2. And here lambda is equal to 3.2 into 10 power minus 2. So this we are going to represent in meters here. So if we substitute this data D, you will get 7.5 into 12 into 10 power minus 2 into 12 into 10 power minus 2 divided by 3.2 into 10 power minus 2 whole square. So if we simplify this, you will get approximately 105.46. 105.46, this is the decimal value. So we need to convert this into dB. So in dB, you can write as 10 log base 10, 105.46. This is approximately equal to 20 dB, 20.123 dB here. So 20.123 dB we are getting. So this is how to simplify the problem. So D is equal to 7.5 AP by lambda square. So AP is given in centimeters. Convert this into meters. So 12 into 10 power minus 2 we are getting here. The length of the E-plane sectoral horn is 15 centimeters. Design the horn dimensions such that if it is optimum at 15 gigahertz. So here the data given is F is equal to 15 gigahertz. So we need to design the horn dimensions. We need to find out the horn dimensions, that is the length and width, length and breadth of the horn. So here rho is equal to, it is given as rho in terms of E, in E direction is given as 15 centimeters. So we can represent it as 15 into 10 power minus 2 meters. And C is equal to F lambda. So lambda is equal to C by F. C is equal to 3 into 10 power 8 divided by 15 into 10 power 9 here. So 10 power 8, 10 power 9 you will get. So 3 ones, 3 5s. So this is equal to 1 by 50 you will get. So 1 by 50 is equal to 0.03 meters here. So this is the value of lambda. So now we need to find out the value of delta here. So delta is equal to 0.25 lambda. Delta is equal to 0.25 lambda. This is equal to 0.25 into 0.03. So we will get 0.75 centimeter. So delta is equal to 0.25, lambda is equal to 0.25 into 0.03. So that is equal to 0.75 centimeters. Now the length of E-plane. The length of E-plane aperture is given by H is equal to root of 8 delta into rho. Root of 8 delta into rho. So which is given by 8 into 0.75 into 15 into 10 power minus 2 into 15 to 10 power minus 2. We can also write this as the root of 8 into 75 into 10 power minus 2 into 15 into 10 power minus 2. So if we simplify this, you will get 0.09 meters. So if we simplify this, you will get 0.09 meters here. So now the flare angle, we need to find out the length of flare angle. So theta is equal to cos inverse of rho by rho plus delta. So the length of flare angle is known as this equal to cos inverse of 15 into 10 power minus 2 divided by 15 into 10 power minus 2 plus delta is equal to 0.75 into 10 power minus 2. So if you simplify this, you will get 17.75 degrees. You will get 17.75 degrees. So this is how to simplify the problem here. So F is equal to 10 gigahertz, rho is equal to length of E-plane, 15 into 10 power minus 2 meters, and lambda is equal to C by F here. So substitute these values here, and you will get H is equal to 8 rho delta. So theta is equal to cos inverse of rho by rho plus delta. Now let us calculate the length of the dipole antenna here. So the length of the dipole, reflector, director 1, director 2, director 3 of the dipole antenna. So to design an antenna, we need to design an Yagi-Uda antenna. So we need to find out the values of the length of the dipole antenna, the length of the reflector, the length of the director 1, the length of the director 2, and length of the director 3. The frequency is given here. So here we know that this is the driven element, and this is the dipole, and this is the director 1. This is the reflector, and this is D2, and this is D3. We need to find out the spacing here between these two elements. So we are having a fixed formula here. So the length of the dipole is given as 143 by F, 143 by 177.5, which is known as 0.8 meters. Similarly, the length of reflector is given as 152 by F. It is 152 by 177.5, 0.86 meters. So similarly, there are formula to find out the length of director 1, director 2, and director 3. That is 137 by F, 133 by F, and 130 by F. So F is given as 177.5. So if you simplify, you will get 0.77, 0.75, and 0.73. Similarly, we are having a formula to determine the length of spacing between the reflector and dipole. So 75 by F, dipole on the director 1 is 40 by F, and director 1, director 2 is 38 by F. So based upon this formula, we need to find out all the values of spacing between the reflectors and the dipoles and the directors. So here, the two identical horn antennas separated by distance of 100 meters. So both antennas have directive gains of 15 dB in the direction of transmission, and the dimensions are 12 by 6 centimeters. The transmitting antenna ends out 5 hours at 3 GHz to determine the received power. So all the data is given here. The distance R is given as 100 meters. The GT is equal to GR. It is given as 15 dB. And here the value of frequency, it is given as 3 GHz. From this you can calculate C is equal to F lambda, and lambda is equal to C by F. We will get the value of 3 into 10 power 8 divided by frequency 3 into 10 power 8. So we need to calculate the value of the transmitting antenna WT is given as 5 watts, and WR you need to find out. So all this data you substitute in this formula. So we need to substitute all the data in the formula. So all the data is given. The distance between the antennas is given as 100 meters. So if you simplify this, you will get the value of WR by substituting all the given data. So for references for these problems, you can refer Antennas Waves and Propagation by U.A. Bakshi and K.D. Prasad Antennas and Wave Propagation, taken in publications 2001. So for more problems, you can also refer Balanis and also John D. Cross. So let us close this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.